we'll be finishing up this afternoon with HUBzero applications and experiences. And the first talk in this session is from Karan Vahi from the Pegasus group at the University of Southern California. So welcome.
All right. Thanks a lot, Michael. Good afternoon. I'm Karan Vahi, a computer scientist at University of Southern California Information Sciences Institute. And I'm here to talk about complex workloads on HUBzero using the Pegasus Workflow Management System. So we all pretty much know what HUBzero and Hubs are. They're a valuable platform for scientific researchers, for building analysis tools and sharing with researchers and educators. Usually the tools are made available to the user community via a web interface. They support interfaces for designing analysis tools, primarily using the Rapture toolkit, uploading and creating inputs, and visualizing and plotting generated outputs. As far as usage of the hubs goes, they run into hundreds of tools and thousands of users. So it's great to have HUBzero be able to scale up to so many users and tools, but at the same time, on the scalability front, the execution of the analysis tools for all users cannot be managed on a single hub instance. So we need to decouple the analysis composition and user interaction layer, which resides in the hub web interface layer, from the backend execution resources. This need for scalability requires a need to support multiple types of execution backends. Your hub may be tied to a local cluster or a server instance itself, or in case of most of the Purdue-hosted hubs, they are connected on the back end to DiaGrid or distributed computational grids as open science grid. So let's say somehow magically hubs can farm out the analysis to these back-end tools. There are a certain set of challenges which are posed to the community. First of all is portability. You can tie your hub to a local cluster, get the analysis tools working, and then later on you decide that you want to use the DiaGrid or the open science grid to manage the execution. So how is the portability managed, where the changes are made? As soon as you start running on different infrastructures, data management becomes a big issue. For example, each of the backend execution resources have their own way of transferring in the data, shipping out the data. As far as the hub user community goes, they're pretty used to some uploading inputs through the web interface and retrieving the outputs or visualizing them in the hub provided web interface. There are a lot of underlying tools to be protocols to be taken care of, like SRM, grid FTP, HTTP, iRods, squid proxies. And as most of you would know who have run scientific analysis themselves, as soon as you hit the distribution part of the process, then the debugging and monitoring of the computation becomes a big challenge. You usually need automated tools to go through a lot of log files. User logs and system logs, they're being created in a myriad of different places. There's a need to correlate the data across these logs. For example, you need to know for debugging purposes, like where did a particular job run and how it was invoked. And some of the analysis tools which are hosted on hubs, they're actually very short running, so they're just a spike. But to be able to effectively distribute them across distributed computing infrastructure, you need a way to restructure the underlying pipeline for performance. So with HUBzero, we took this approach of separation of concerns, where the HUBzero layer focuses on the user interface and provides users means to design, launch analysis tips, inspect and visualize outputs. The analysis tools themselves get modeled on the back end as scientific workflows, and we'll use a workflow management system such as Pegasus to manage this computation across varied execution resources. So we want to keep the core hub functionality, which focuses on the user UI, the Rapture toolkit, and the interaction, and then decouple the execution of the analysis that is launched as part of these tools using Pegasus workflows. So what are scientific workflows? They're actually fairly simple. They orchestrate complex, multi-stage scientific computations. More often than not, they are expressed as directed acyclic graphs of tasks that need to be executed, and they capture the analysis pipeline for sharing and reuse. I have an example of an epigenomics workflow below, which highlights how complicated or simple a DAG-based workflow can be, where we have a single first job, which is a setup job, then it splits the input files coming off the sequencer, and then you do a series of analysis steps, and finally merge the results back and analyze them and make them available to the user. So Pegasus is a workflow management system which we've been developing at University of Southern California since 2001. It's a close collaboration between USC and the Condor team based at the University of Wisconsin-Madison. So Pegasus sits on top of Condor Dagman and relies on Condor Dagman as a workflow executor and other Condor layers to do the actual job submissions. Pegasus is able to map abstract workflows across diverse computing infrastructures like a desktop, a local Condor pool, HPC cluster, grid, or cloud environments. I'll be getting into what abstract workflows mean in a couple of slides. And as far as the usage of Pegasus goes, it's used fairly widely by many applications in a variety of domains, ranging from earth sciences, physics, astronomy, bioinformatics. So what benefits do the notion of workflows give to Hub community? First of all, there's a clean separation of users, the developers, and the operator. So for the users, there is a nice high-level interface provided via Rapture. The tool developer, in this case, the person developing the Rapture toolkit, they only have to build or provide a description of the workflow, and then the Hub operator ties the Hub to an existing infrastructure using the submit tool, which is part of the core functionality of HUBzero and developed at Purdue. So the Hub submit and Pegasus combination handle all the low-level details about job scheduling, data staging, job retries, workflow analysis, and support for large workflows. And where the Hub submit tool comes in handy is it does the setup of Pegasus for you automatically for a variety of different execution environments. So as a Hub user to use Pegasus workflows via the submit interface, it's pretty much like a very low-hanging fruit for developers to use. So Pegasus workflows, they are directed acyclic graphs. What I mean is nodes are tasks. Typically, they're executables with arguments, and each executable is associated with a unique logical identifier. For example, let's say you have some fast Fourier analysis that you want to do in that node. So you'll call that node is identified by FFT. Nodes can also be other workflows. That's how we scale up to really large hierarchical workflows where jobs can have an order of 1 million tasks. And the workflow descriptions is file aware. With that, what I mean is that with each node, as a user, you specify the input and output data sets referred by logical identifiers. The edges in the underlying DAG refer to both control flow and data flow dependencies. By control flow, we mean that a job can only execute when all the parents have successfully finished. And a data flow dependency in this case is that a parent job may be generating some outputs which a child job requires. And if you're executing these jobs across distributed infrastructure, then we need to manage the transfer of data in between the jobs. The DAG-based approach doesn't support any loops or branches directly. Recursion is possible via the notion of a node being a workflow itself. And we can conditionally skip tasks with the wrapper, but more often than not, in our user community and most of the scientific community, this is not a big deal breaker. So this abstract workflow description, it captures the computational recipe devoid of resource descriptions and devoid of data locations that is portable and can be easily shared. So the workflow that you described to Pegasus is how you would imagine your computation to occur in your mind, that I need to do these series of steps in this order, and they require these files, without really referring to where the files are or where the codes that are required to run these particular nodes exist. So my next slide has this notion of like a simple two-node hello world workflow, which is what your analysis is, which you need to execute, let's say, on Open Science Grid. So you give this to Pegasus, and Pegasus will act as a workflow compiler and take this abstract workflow and generate an executable workflow that can actually run on a particular distributed computing infrastructure. So as a process of this workflow compilation step, in this canonical example, what Pegasus will end up doing at runtime is, first it will figure out where these jobs can run. So it pins the jobs to a cluster. Let's say, like in this case, Open Science Grid appears as one execution site for Pegasus. Then looking at the description, since as a user you already specified what inputs and outputs each job requires, Pegasus is able to look up data catalogs at runtime to figure out where do your actual input data sets reside. So it will select a best replica for the execution and add a parent data staging node, which will be responsible for staging in the data to the remote site at runtime. Similarly, as the outputs are created, we have data stage out nodes added, which stage the data back to the hub instance for the outputs to be made available to the final user. It's a graph-based description, so we're able to identify at what points we can do data cleanup. So we remove files that are no longer required by adding these additional data cleanup nodes. Now, in this canonical example, you see that there's a two-node workflow exploding to like 8-node workflow, but there is not always this one-to-one mapping. For larger workflows, the data staging nodes are constrained for performance reasons, and basically your workflows don't expand as much as in size as this example might indicate. So this abstraction, as you can see, provides a couple of things. There's ease of use. When you're, as a researcher, thinking about your analysis pipeline or computation, you do not have to worry about the low-level execution details. So for you to describe your computation or pipeline to someone else, you just say that I have a two-node pipeline that needs to be executed. It requires these inputs, generates these outputs, and that's it. Then there's the portability aspect. Once, as a developer or a user, you modeled your pipeline as a Pegasus workflow, then you can move from one candidate execution environment to another without changing the description at your end. So let's say you have a complicated genomics pipeline that needs to do a large series of analysis. You have modeled that as a Pegasus workflow. You can run it on a local cluster one day, on Open Science Grid the other, and then an Amazon EC2 the other. So all the data management aspects of like shipping in the data, et cetera, will be managed by Pegasus. This description of this compilation phase gives us opportunities for optimization and fault tolerance. So we can automatically restructure the workflow and provide fault recovery, for example, retries in case of failures. On the data management aspect, one of the most important guarantees which Pegasus gives to the developers is that irrespective of wherever or whenever your job executes, its inputs as described in the abstract workflow description will be made available in the directory in which the job is launched. So let's say you're running on a cluster where there's no shared file system. It's Pegasus' job to figure out that when your job launches on a worker node, how do the inputs appear? Whether we do it through job wrappers or lightweight Pegasus instances, that's hidden from the end user. So as part of this process, one of the key beneficial features of Pegasus is the data management aspect which we provide to our users. And by that, we mean being able to execute your tools in a varied different infrastructures which are architected differently. For example, the most canonical high-performance computing case is a shared file system setup. For example, you want to run your pipeline on a Rossmann cluster. There's a shared file system. Worker nodes and the head node have a parallel file system with great I/O characteristics. So in that case, we can leverage notion of symlinking against existing data sets which already reside on your cluster so as to prevent multiple copies for the job. Or on the other extreme end, there's not a shared file system between the nodes. For example, if you have heard of Open Science Grid, then in that particular case, a variety of clusters are tied together into a large computational grid, but they don't have a shared file system set up across the nodes. So in that particular case, the execution nodes are decoupled from the staging servers which Open Science Grid provides, and that's the similar model which is followed in whenever you try and run something in a cloud-based environment, where you would want to use these cloud-provided object stores, but as a user or a developer, you would not go the hassle of setting up a shared file system across your running virtual instances at runtime. So for example, HUBzero uses Pegasus to run a single application workflow across sites, where on the local cluster, they leverage the shared file system, and then other jobs are farmed out to Open Science Grid. So this mix and match capability helps addresses users' needs of running in different infrastructures. Then in case, let's say, you don't have any data staging server available or access to, since we sit on top of Condor, we can leverage native Condor file mechanisms also for staging data products. So independent of these approaches, Pegasus also supports a variety of transfer protocols for directory file creation management, such as HTTP, SCP, Grid FTP, iRods, cloud-based storage as S3 or Google Cloud Stores, Condor File I/O, local file copies, OSG Stash. And using Pegasus, we allow you to move from one deployment to another without changing your workflow description. So another thing which Pegasus is able to do more as a compiler type thing is workflow reduction or data reuse, where the premise is, let's say if you have a long-running analysis pipeline and it fails midway because of errors, so what options does Pegasus provide to our users to do failure recovery? So one is, you can just start from where you left off, or we can also do more sophisticated file-based recovery, similar to a make-style functionality when you compile large software systems, where intermediate data products or intermediate files of your pipeline which have been successfully generated, Pegasus can reason that they already exist, and hence parts of the underlying DAG don't need to be executed. So in this example, for example, there's a file f.d, which the job D generates. Let's say that existed somewhere and Pegasus was able to discover its location. Then at runtime, it can reason that I already have an output for this particular job. so I don't need to execute that. And then hence, it will also reason that it doesn't need to execute job B, so it prunes away this computation. And this really proves very useful when you've done part of the computation and then realize you need to change the actual underlying structure of the analysis pipelines. So some of our users, when they run Pegasus-based analysis pipelines, they run for a couple of weeks across hundreds of nodes. And we've encountered instances where they set up the pipeline incorrectly. For example, some arguments were passed incorrectly. So they use this approach to change the complete workflow description underneath and then seed it with the workflow products that were generated successfully. Another thing which probably in the hub context people don't encounter that much, but it's a problem when you're running lots of workflows on a particular cluster is you would run out of disk space during workflow execution. Why does it occur? Because either your workflow is bringing in huge amounts of data, or data is being generated during the workflow execution, and users are lazy. They don't really worry about cleaning up after they have done. So there are multiple ways to go about this problem. One is, Pegasus in its executable workflow generation phase can add up a cleanup node, a leaf cleanup job to the workflow so that all the intermediate data products get removed once a workflow succeeds. Or you can also interleave cleanup automatically during workflow execution. This requires an analysis of the underlying DAG structure to determine when a file is no longer required. So that's one of the algorithms which we already have incorporated into Pegasus and is available to the users all the time. And then, we have to cluster the cleanup jobs for large workflows for performance reasons. So a couple of real-life examples. We had a UCLA genomics researcher who was trying to run this big Vervet monkey sequencing pipelines on a local UCLA cluster, but his workflow generated required more storage than was available on the scratch file system of that cluster. So basically, that researcher used this functionality to remove the intermediate products which are no longer used automatically. So on the left, we have a simple canonical example where that hello node example I showed earlier, and there are 2 or 3 cleanup nodes added on the right. On the right-hand side, I have a graph of a real sequencing pipeline that's run through Pegasus out of the Soya KB project of iPlant, where a single workflow requires about 3 terabytes of data. But by leveraging Pegasus' ability to automatically interleave cleanup with the execution, we are able to cap the peak storage required at about 1.5 terabytes. And then you can see as the workflow goes to completion, finally the disk space that is used by the whole workflow approaches 0, because your outputs are transferred to your server, and then all the scratch space used gets automatically deleted. All right, looks like. Another issue which happens and which also occurs in case of a lot of analysis tools provided out of Hub. And they may be running a series of different executables, but they themselves are very short running. So you want to farm them out to back-end distributed infrastructures for computation and scalability. But at the same time, you don't want to, achieve a compromise in the workflow turnaround time. Why does that happen? Because once you go down this road of running things remotely, then each job has a scheduling overhead. You need to make this overhead worthwhile. So in Pegasus, we support ways of clustering short-running jobs together automatically for users. Another thing which Pegasus provides is the ability to monitor and report back to the users what went wrong. For example, we launch a monitoring daemon automatically that goes through the various Condor logs and populates them to a SQLite database. And then we provide tools for querying the monitoring framework like Pegasus status to get the status of your current workflow, figure out what jobs are running, how many have completed. Pegasus statistics gives you runtime provenance information as to how much compute resources your workflow took, what was the wall time. All this is integrated into the Hub infrastructure via the Submit integration. So Submit provides this into the Rapture UI by calling out to the Pegasus provided tools. Things cannot be expected to be run reliably all the time. So the other part of the monitoring story is workflow debugging. And even for that, through Pegasus, we just provide a simple command line client which can go through the workflow logs and tell you exactly what jobs failed and why they failed. For each job, we will be able to show you its last known state, the exit code, what node a job ran on, the working directory, and any std out, std that your executable pointed out. Std out, std logs that your executable is associated with. So this is also already integrated with this Submit tool provided out of HUBzero. You don't have to do anything, and you leverage it. So I've given you guys a high-level overview of some of the feature sets which Pegasus provides. And now I'm going to shift gears and talk a bit about the HUBzero Pegasus integration, where how a tool developer can use Pegasus to go do this. So how would you generate a workflow? You have a couple of ways to go about it. One of the ways, if you're using the Rapture toolkit, is to have a tool description file that specifies a Python run script, which is called a driver file, that gets invoked by the interface when you hit a submit button of any of the Rapture tools. So in that, by default, Rapture calls out to this wrapper.py Python script, where you can have a call out to a Pegasus Python DAX API to generate your workflow description or encode the code in there itself. The other option is, if you're familiar with command line interfaces, then just launch the workspaces tool on your hub, get a terminal window, invoke your code to generate the workflow description, and then use submit to submit it for execution. So this next slide captures this model at a high level, where we have a tool developer like Chris, who developed this Plast tool on HUBzero. So he will take the Rapture toolkit description and the wrapper.py, and the logic is pretty much, prepare the inputs, launch the workflow, and present the outputs. As far as the users go, they interact with the hub. They use the Rapture provided interface to prepare the inputs and configure the Blast pipeline that when you hit on the submit button, gets invoked through wrapper.py, and a Pegasus workflow description gets generated automatically, which gets submitted via the hub to Diagrid or Open Science Grid clusters. And then Pegasus provides this monitoring information back to submit, which is incorporated into the Blaster Tools UI. And finally, when the final outputs are created, they are available for inspection through your Rapture-based toolkit. So the next slide goes a bit deeper into the execution part of the workflows, which even the tool developer doesn't really see. But I just want to have this slide to highlight that if you're trying to run on a distributed infrastructure, then how does the data management happen out of your workflows? So as a user, you're uploading input files through the Rapture web interface. That's the only entry point you have for as a user. Pegasus takes in the workflow description, generates an executable workflow where we have these data staging nodes added, which will move the data first from the hub instance to OSG staging element, which can be grid FTP server or SRM or an iRODS instance. And then each of your jobs get wrapped with lightweight Pegasus Lite instances, and underneath they get matched to a node in the Open Science Grid or your cluster at runtime. And when the job starts, then the lightweight Pegasus instance grabs the inputs from the staging area element, launches your code, pushes the generated outputs automatically back to the staging element, and then finally the data stage out jobs will take the data from the staging element and bring it back to the hub instance where it can be displayed through the Rapture interface. So all this sort of complicated data flow is hidden from any of the Pegasus users, but is happening in the back end. And again, it's complicated in this case because we don't have a shared file system. If there was a shared file system, we can optimize and not have these Pegasus Lite instances. And all that happens automatically. So to highlight how you can use Pegasus through Submit, we do have a Pegasus tutorial tool available in HUBzero called PegTool. It's a very simple two-node workflow, which I described earlier, where here this is a Rapture definition, which users use to define the inputs and specify the tools that are being used. Then there's this wrapper.py, which your Rapture generated tool calls out to. So this Python script is the glue between the Rapture interface and user. So it collects data from the Rapture interface, writes it to a file, generates the workflow description, and then submits the workflow using the submit command, which HUBzero provides. The use of submit is pretty beneficial because it automatically generates these descriptions for Pegasus to know where on the hub instance it can stage the data products from or stage the outputs back. So as far as the Rapture based, like the workflow definition goes, so if you're a Python programmer, this is an example of a two-node Python, a two-node workflow that is using the Pegasus provided Python API to describe the workflow to Pegasus. So it just says, I'm creating an abstract workflow, say hi inquire. I give information about the input file, where it resides, that's somewhere on the hub instance. It refers to executables on the hub instance that can run these codes, adds the jobs, links them together, and finally tells the final output. And Pegasus treats executables as data. So when you're running anything on a remote resource, your executables or scripts do get transferred by the system automatically. Like on Open Science Grid, you have no way to log into a cluster or a node and pre-install your executable. So you have to ship the data and executables along with your job. So these are some screenshots from this Pegasus tutorial tool where user provides the inputs to the workflow and then clicks the submit button. When the submit button is clicked, it launches the workflow. Once the outputs have completed, they're made available. So in the drop-down box, you see all the files which a particular workflow refers to and is made available for browsing and downloading. So I'll give a brief introduction to the submit command. It's used by the Rapture interface to submit the workflow. In tandem on the other tracks, there is a submit and a Rapture tutorial going on which goes into detail about how to use this. Submit tool allows Hub users to submit workflows through Pegasus to Open Science Grid, Diagrid, and local clusters to which your hubs may be tied down to. It automatically prepares the site catalog and other configuration files for Pegasus, uses Pegasus-provided monitoring clients to track the workflow and report the status back to the user using the Rapture interfaces. So some usages of Pegasus in hubs. In fact, till a week back, I myself did not know like how many hubs were using it. And there are a fair number of tools which we have, which are actively using Pegasus without the users realizing. So you have a way of using Pegasus using workspaces. All hubs have Pegasus and Submit installed and configured on the nodes. So if you don't want to develop a tool and want to get your hands dirty with the command line terminal, you can be up and running in no time. In Nano Hub, we have CFNetLab, NanoFit, Nanoplasticity tools already configured to use Submit and Pegasus. On Diagrid, we have the Blaster toolkit, which Chris will be talking about next, to run jobs on the Diagrid hub. We have Cryo-EM tool and Submit-R. And then we also had these OpenSeas workflows running out of Nice Hub. Here's another example of like the Nanoplasticity tool in Nano Hub where like you don't get any notion that the tool's actually running workflows at the back end or it's running in a distributed environment. So you have, you can specify and configure the simulation through the tool UI, which has been built using the Rapture interface. Once the workflow starts executing, the tool just provides the status back using Submit. And as the outputs are generated, the outputs can be inspected in the tool-specific UI. So Rapture-based tools, they're built using the Rapture GUI tool, builder. Users configure the simulation, prepare inputs, and then the job execution happens through Submit and Pegasus. And finally, it allows users to visualize the outputs in the tool UI. So we already have tools in Nano Hub, Diagrid, and Nice Hub, which are actively using Pegasus. Some relevant links. So Pegasus website has a lot of information about Pegasus itself. And the HUBzero documentation talks a lot about the Rapture and Submit interface and about how Pegasus workflows on HUBzero work and the link to the tutorial tool on HUBzero. Right? Thank you.